6 friends will exchange books in their book club. Each friend has one book to give to a friend and will receive one book from a different friend. No 2 friends trade books with each other. In how many ways can the books be arranged? The challenging aspect of this question is that there's 2 scenarios. If there was only one scenario, I think it would be a little bit easier. But unfortunately, there's 2 scenarios. So I've got 6 friends, so I'm going to label them A, B, C, D, E, F, A, B, C, D, E, F. And since there's 2 scenarios, I've got to explain this in 2 different ways. So 2 circles. Okay. So let's start with, I don't know which one is easier. It doesn't really matter, but let's just start with this one here, the one on the right. Now, in that circle, I have to somehow satisfy the conditions of the question. So let's start off. A is going to give a book to B. Okay? But then A has to receive a book from somebody, but he cannot receive it from B because no 2 friends trade books with each other, right? So, okay, let's just keep going. B gives a book to C. C gives a book to D. Okay, you get the point here, I hope. D gives a book to E. E gives a book to F. And then finally, F gives a book back to A. This is a legitimate scenario where it's all just kind of going round and round. That's just one, though. One of many. As you can see, there's answer choices are pretty large. This is just one. So, for example, if the answer was 200, this is just one of 200 scenarios. We have to figure out how many. So how do we do that? Obviously, we're not going to write out 200 or whatever the answer is. So then we look at this and say, okay, what are the possible choices? So, for example, if I started with A, I made a diagram that went to B. But what other points could A go to? Who could A give a book to? That's what that represents. Well, initially, he could give a book to either B, C, D, E, or F. So he's got 5. He's got 5 choices. So I put a 5 there. 5 representing the number of possible ways he could move forward with his book giving. Then you get to B. How many choices does B have? Well, in my diagram, I made B go to C, right? That's legitimate. But B can also give a book to D. I could have done it like that, right? He could also give a book to E. I could have drawn it like that. He could also give a book to F. I could have drawn it like that. But he cannot give a book to A. Why? Because no 2 friends can exchange books. Since he received a book from A, he cannot give a book back to A. So for B, it looks like there was only 4 choices. So I drew 1, but there's 4 possible ways of B giving a book. So let's now go to C. C, I drew it in a way that he's giving a book to D, right? But he could also have given a book to E. I could have drawn it like that. Or he could have given a book to F. And he can give a book to F. But he cannot give a book to A in this scenario. Now you say, well, why not? Well, because remember, one of the ways of A giving a book was to C. I didn't draw it in, but that's one possibility. So if A gives a book to C, C cannot give a book to A. Does that make sense? So that means for C, it's just 3 possibilities. Now let's talk about D. I drew it, that D is giving a book to E, but D could also have given a book to F. And in a very similar way, that's the only possible choices for D. And then for E, it looks like E can only give a book to F, and that's it. So there's 1, and then F by default has only 1 person to give a book to. So this is the total. So to figure out the total number, you have to multiply them 5 times 4 times 3 times 2, and then times 1 times 1, but that doesn't affect the product, and this is 120. So from the first scenario, you get 120. So that takes care of case number 1. Now we turn our attention to case number 2. They say, well, how could case number 2 be different? Seems like case number 1 was pretty complete. Well, here's the story. It breaks up into 2 groups of friends. these three and these three. They only exchange books within each other, and I'll show you how. A gives a book to B, right? Then B gives a book to C. And then C gives a book to A. And that is their scenario. Similarly, F gives a book to D, and then D gives a book to E, and then E gives a book to F. That is another scenario, perfectly legitimate. Now we have to count up the number of cases. A is going to B. A is giving a book to B. That's how I've drawn it. But he could have also given a book to C. Or D, or E, or F. Now, I know that's a little confusing. You say, well, I thought you said they were separate. They are. But what I'm saying is that this B could have been any of these letters. I just grouped it like that. So A could have given a book to B, or could have given a book to C. But I could have also, instead of B, I could have put a D. You see what I'm saying? Right here, this is B, but it could have been a D. So that means that A could have given a book to D also. Or instead of putting D there, I could have put E there. Or instead of putting E there, I could have put an F there. So as you can see, any of the 5 could have started off that little chain. So that means this has 5 possible ways of being done. A to B or C, D, E, or F. Okay, I hope that makes sense. And then once you have B, B is going to give a book to C, right? So I've written like B to C. But instead of C, we could put here D, or we could put E, or we put F. So there's 4 possible choices for that letter. And therefore, this is 4. Now, once you have that, interestingly, now you've got 3 friends, and then C has no choice but to give a book to A. So that by default is just going to be one possible choice. And that's it. Once you've selected a group of 3 friends, they just kind of go around like that. In an identical way, this is 5, this is 4, and this is 1. So that's probably slightly more difficult to come up with, but I sincerely hope that you understand that. So now we got to figure out the product. From here, it's 5 times 4 times 1. And then from here, we have another 5 times 4 times 1. So that means that's 20 plus 20, and that is 40. So we got 40 here, we got 120 here. So the grand total, if you add those two, is 160. So number 24, the answer is E. In any triangle, the length of the longest side is less than half of the perimeter. All of the triangles with perimeter 57 and an integer side lengths x, y, z such that x is less than y less than z are constructed. How many such triangles are there? We have a few rules to follow. I'll put those rules here on the side. The first thing, of course, very important, is that these sides are in this kind of relationship. X is less than y, y is less than z. And then the perimeter, of course, is the sum of those is 57. And another thing they told me is that the longest side is less than half the perimeter. So the longest side for us is z, and it's less than half of the perimeter. The perimeter is 57, so z is less than 57 over 2. 57 over 2 is what, 28.5? So z is less than 28.5, but z is an integer, so z must be either equal to or less than 28. Okay, so these are some very important rules that we are going to have to abide by when creating these triangles. So here we go. The first one I'm going to do is, let's see, where do I want to start here? Oh, let's just start with z equals 28 and just keep going down. Might as well make it easy. So let's look at the first one, which is when z is equal to 28. When z is equal to 28, that means that since x plus y plus z is 57, x plus y plus z is 57. If z is 28, plug that in, and we therefore get that x plus y must be equal to 57 minus 28, which is 29. So we have to create a table where z is 28, but x plus y is 29, and we have to make sure that they are in that inequality. So here is my first table. This satisfies everything, that z is 28 here, x plus y is 29, and that's pretty much it. And then the rest of the values for x and y I've put here, and as you can see, those are the values, and there's a total of 13 of them, so I'll put 13 out here. Now these values all satisfy the fact that x minus y, or x is less than y and y is less than z. Now you might say, well, you skipped over a 1. How about x equals 1? Why didn't you put x equals 1 in there? Well, because if x is 1 and x plus y is 29, then y would be 28. And you can't have y equals to 28 because z equals 28, and y has to be less than z, right, according to this inequality. So I have to abide by a certain set of rules here. The first rule, of course, is this one, then this one, and then now this one. Once you subtract z equals 28 from the perimeter, x plus y is 29. So I really wanted to, ensure that you understand how this table was created. Okay? And when you did, you got 13 possible sets for x, y, and z. Okay, now we move on to the next set. The next set is when z is 27. We're going down, right? We're going down from 28. Now when z is 27, and then you plug z into this equation right here, you get x plus y is equal to 30. So again, exact same thing. We have to make a table with values for x and y, abiding by these 3 rules. And when you do, you get this table right here. And that table gives me 11 additional values. All right, let's move on to the next one. The next one is z is equal to 26. Now x plus y will be equal to 31. And again, same thing. We have to ensure that x is less than y and all that stuff. And when we make that table, we get this scenarios, and that gives me an additional 10. Now let's keep going. Z equals 25. This times x plus y is 32. And again, I make the table, and this gives me 8. I go to z equals 24, and this time x plus y is 33. And that means we have another 7. There's no real pattern. You think, well, if it was always just 1 down, 13, 12, 11, then you can just add them all up. But it kind of jumps around here. There doesn't seem to be a distinct pattern. All right, no problem. Let's keep going. When z is 23, x plus y is 34. And again, you make that table, and you get 5. If you go down to z equals 22, you get x plus y is 35, and now you have only 4. When z is 21, you get x plus y is equal to 36, right? Yeah, 36. And there's only 2 in this table this time. And the last one, interestingly, is with z is 20, x plus y is 37, and you only have 1. Now you might say, well, why didn't you just keep going? What about z equals 19? Why did you stop? Well, when z is 19, x plus y would be equal to 39. 38, sorry. And if x plus y is 38, then how am I going to make it so that x is less than y is less than z? If, for example, if I chose x equals 19, then y would have to be 19. And you can't have both of them equal because one has to be less. If I said, okay, fine, let me choose x equals 18. If x equals 18, then y is equal to 20. And, well, that doesn't work because y has to be less than z. You see what I mean? So once you get down to z equals 19, there's no way to make that work. So that's where we stop right here. Okay, so all we got to do now is take a look at our values and add them up. All these values that I circled: 1, 2, 4, 5, 7, 8, 10, 11, 13. And when you add up all those, you get 61. 61 for this question, and that means number 24, the answer is B. Each face of a cube is painted with exactly one color. What is the smallest number of colors needed to paint a cube so that no two faces that share an edge are the same color? Well, let's draw a cube and let's talk about this. Well, let's see. You have to remember that each face has obviously 4 edges, right? So we know that if you have one face, let's say it's red, then none of those other 4 can be red. So that's the first thing to consider. And when you fiddle around with this, you realize that you can have a scenario as follows. You can have red, for example, as the front, and red as the back. B for back, F for front. We can have another color for top and bottom. Let's just say it's blue. Blue for the top and blue for the bottom. And then we can have another color for the sides. We can have green here on the left, and we can have green here on the right. And if you do it like that, you'll notice that the conditions are met, that no two faces that share an edge are the same color. And that's accomplished with just 3 colors. So number 22, the answer is B. Lucas chooses 1, 2, or 3 different numbers from the list 2, 5, 7, 12, 19, 31, 50, and 81, and writes down the sum of these numbers. If Lucas chooses one number only, this number is the sum. How many different sums less than or equal to 100 are possible? We have a list of 8 numbers. So if there's only one number, then from those 8, you just choose one, and that's 8. So 8 is the start of the different sums, and the sums are right there. Those sums, of course, would be 2, 5, 7, 12, 19, 31, 50, and 81. Okay, that one is easy. What if you choose 2 numbers? Then from those 8, you have to choose 2. 8 choose 2 is 28. But we have to account for the fact that there could be some doubles, and there could be some that are greater than 100. We want less than or equal to 100. Okay, so the ones where there's 2, it wouldn't take that long to figure it out. So we got 2 and 5, right, which is 7. 2 and 7, which is 9. And then 2 and 12, which is 14. 2 and 19, 21. 2 and 31, 33. 2 and 50, 52. And 2 and 81, 83. And in a very similar way, 5 and 7, which is 12. I'll just write them all out. I don't think you need me to voice them all out. So I'll just make the list. And then now we get to the one where we're combining the 7 and the ones. So 7 and 12, 19, and so on. 26, 38, 57, and 88. And then now we use the 12 to combine them. So 12 and 19, that's 31, and 43, 62, 93. And then 19 plus 31, that is 50, and then 69, and then 100. And then we're up to now 50, or 31, I should say. 31 and 50 is 81. And then we have a 112, and then finally 50 and 81 is 131. Okay, so this is the list. When we have 2, this is the full list, and it should be 28. Now what we have to do is eliminate the ones that are greater than 100, because that's not less than or equal to 100. And it looks like there's only 2 of those that we eliminate. Now we have to get rid of any doubles, any number that has already appeared, because we want different sums. We want unique sums. How many different sums less than or equal to 100? So if it's counted twice, we don't want that. Well, the 7 has already appeared here. Let's see what else. The 12 already appears here. The 19 already appeared. The 31 already appeared. The 50 appeared. And the 81 appeared. So these ones we have to get rid of. So 1, 2, 3, 4, 5, 6, 7, 8. So from that 28, we have to subtract 8. So therefore, we have 20. 8 and 20. So far, those are the unique sums. Now, we have to do the same thing this time for 3. Now, for 3, it will seem quite time-consuming, and it is. But the good news about this question is that there's a shortcut. We have 3 numbers now. Well, 3 numbers is 8 choose 3. 8 choose 3 is actually 56, so that's a pretty big number. Quite a few combinations. But the good news is, due to the nature of this list, any sums that involve consecutive numbers will end up as a repeat. So let me give you an example of what I mean. Let's say I said I want 3 numbers, and I'm going to choose 5, 2, and 7. Right? Those are all consecutive. And I add those up, and the sum would be 14. Well, 14 is already included. So that would not give me a unique sum. Okay, let's try 2, 5, and let's go a little bit farther down. 31. 2, 5, and 31, that's 38. And 38 is already included. Okay, let me get away from this 2 and 5. Let's see if I can do this. Keeping in mind that I guess the undesirable way of doing it is having consecutive. So let's see what happens if I choose consecutive again. 12, 19, and 30. Let's choose 50. 12, 19, and 50 is 69 plus 12, which is 81. 81's already there. So I hope you can see that having consecutive numbers will result in giving you something that's already been created. So the rule is that we're going to choose 3 numbers that are not consecutive in order to get unique sums, unique new sums. So to repeat, due to the nature of this list, any new sum must come from 3 numbers, no 2 of which are consecutive. And if we do that, it considerably kind of reduces our time, because this is a time-consuming question. So instead of 2, 5, those are consecutive, so I got to jump at least to 7. And then after 7, I can't choose 12, I have to choose 19. So that's how I'm going to make my life. So 2, 7, 31, 2, 7, 50, 2, 7, 81. And then very similarly, 2, 12, 31, 2, 12, 50, 2, 12, 81. And then 2, what's the next one? 19, 50, 2, 19, and 81. Okay, we've exhausted the 2's. Let's move up to the 5's. So we got 5, can't choose 7, 12, can't choose 19, 31. See how I'm doing it? I can't choose 2 consecutive numbers, because if I did, it would give me a number that it would give me a sum that I've already obtained. So 5, 12, 81. And then now let's move up to the 19. 5, 19, 50. 5, 19, 81. Okay, I've exhausted the 5's, and I'm up to the 7's now. 7, 19, 50. 7, 19, and 81. And then I'm done with that. Now I'm up to 12. 12, 31, and 81. And I think that's it. That's the end of the road. Okay, that's good. So I didn't have to do 56. I only had to do whatever this is, probably about 15 or so, 16 maybe, whatever it was. Okay, now let's figure out the sums. So this will be 28, 40, 59, 90, 45, 64, 95, 71, and 102. 48, 67, 98, 74, 105, 76, 107, and this is 124. Okay, so first let's eliminate the guys that are greater than 100 because that's outside our range. And then now we have to look, are there any doubles? And there will not be. I don't need to even worry about looking at this list and trying to see are there any doubles because I did not choose any two that were consecutive. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, this one's also greater than 100. So don't include that one. So you just got to be a little careful. So that's 13. All right. So I have 8 up here, 20 here, and 13 here. So my total 8 plus 20 plus 13, and that is 41. 41 is the answer to number 24. That would be E. A positive integer is called multiplicatively perfect if it is equal to the product of its proper divisors. For example, 10 is multiplicatively perfect since its proper divisors are 1, 2, and 5, and it is true that 1 times 2 times 5 equals 10. How many multiplicatively perfect integers are there between 2 and 30? The first thing I'm going to do is list all the numbers between 2 and 30. All right, here we go. Let's go through these one by one. Now, the first thing I want to do is eliminate certain ones that obviously will never work, and those are the prime numbers. And the reason is because prime numbers, as I'm sure you know, have only divisors such that they can only be divided by 1 in themselves. Now, in this definition in the question, they are not including the number itself. Did you notice that? 10, for example, they only included 1, 2, and 5. They did not include 10 as a divisor. So if you look at any prime number, its factors are only going to be 1. So for example, for 29 is a prime number, right? And 29's prime factors are 29 and 1, but they are not including the number itself. That's a little tricky, not extremely tricky, but a little tricky in the question stem. So that means instead of 29 and 1 as its divisors, I only have 1. That's it. So 1 by itself only gives me a product of 1, which obviously is not equal to 29. So I can get rid of all the prime numbers because they all face the same scenario. So let's see, the prime numbers are 3, 5, 7, 11, 13, 17, I think. Is that a prime? 19, 23, and 29. All right, so that was good. Helped us eliminate quite a few. Now let's go through this case by case. 4. Form the divisors not including the number itself are just 2 and 1. Now, when you multiply 2 and 1, does it give you 4? It does not, so cross out 4. How about 6? Its divisors are 3, 2, and 1. When you multiply those, does it equal 6? And the answer is yes, it does. So 6 is one of my multiplicatively perfect numbers. All right, let's keep going here. What's the next one here? 8, right? 8, the divisors are 4, 2, and 1. When you multiply those, do they give you 8? And the answer is yes, they do. So circle that one. So you see, you get the hang of it. And I'll just keep doing this here. For 12, the divisors are 6, 4, 3, 2, 1. If you multiply all of those, they will certainly give you a number much greater than 12. So 12 is out. I think I skipped 9 here for some reason. I don't know why I did that. All right, well, 3 and 1 are the divisors for 9, and 3 times 1 is not equal to 9, so 9 is out. 10, they actually give you in the question, right? They give you that as part of the question. That's one they sort of just handed to you for free. All right, we don't have too many more. Let's just keep going. 14, the factors are 7, 2, and 1. Do they multiply to 14? And the answer is yes, they do. And let's see, next one is 15. The factors are 5 and 3 and 1. When you multiply them, they do indeed equal 15. The next one is 16. Its factors are 8, 4, and 2. And when you multiply that, it will be much greater than 16, so 16 is out. 18 is the next guy. Factors are 9, 6, 3, and 2. When you multiply those, it's going to be much greater than 18, so 18 is out. 20. Its factors are 10, 5, 4, and 2. When you multiply all those, it's going to be greater than 20, so that's out. Next one is 21. Its factors are 7, 3, and 1. When you multiply those, you get exactly 21. So that's another one. Next one, let's see here, 22. Its factors are 11 and 2 and 1. You multiply those, you get 22. So that's one to include. 24, its factors are 12, 6, 4, 3, and 2 and 1. And obviously, when you multiply those, you get much greater than 24. 25, its factors are just 5 and 1, and that won't work. 5 times 1 is just 5. 26, its factors are 13, 2, and 1. When you multiply those, you do indeed get 26. So that's one to include. 27, its factors are 9, 3, and 1. When you multiply those, you do indeed get 27. And the last one is 28. Its factors are, let's see here, 14, 7, and 2. And when you multiply those, you get a number greater than 28. So the ones I circled are the only ones. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So number 22, the answer is A.